Hello, I'm Tom Lin. I'm the session chair for this segment. So I'm going to introduce Lauren Stewart from Intel. He's going to talk to us about Intel SHMEM. All yours.
Thank you and good afternoon. Dave and Wazi elected me to give this, so we'll see how it goes. As is often the case, sometimes Intel has these disclaimer slides we have to use. You can read it later. What I'm going to talk about is kind of what is SHMEM and what is partition global address space programming. Sort of where that is, because it may not be familiar. Then I'll talk about Intel SHMEM itself, what's in the first release. I've got a couple of short examples of how one might use Intel SHMEM with SYCL programs. I'll briefly mention performance, and then I'll just mention the existence of other programming libraries that are useful for distributed GPU programming. So SHMEM goes back to the 1990s from Cray. It's a kind of a lightweight programming model where one does puts and gets to memory on different compute nodes. Essentially, it provides one-sided communications and collective communications, which are the broadcast and gather and reduce that are familiar from anyone who's used MPI. Intel SHMEM implements this one OpenSHMEM API, plus it has some extensions for use on GPUs that let you initiate SHMEM operations from SYCL code and let you talk about GPU memory as well as host memory. SHMEM, as a general thing, supports remote memory access, namely puts and gets, remote atomic operations of the add, XOR, and fetch and add, atomic exchange, that sort of thing. And it has collective operations and synchronization operations, the usual set, broadcast, reduce, all-to-all, gather. And in the case of Intel SHMEM, the API is available both for use from the host and from inside SYCL kernels on the device. And I think the whole point here is that it's a rather lightweight way to add distributed capabilities to your SYCL and GPU programs so that you can expand beyond a single GPU. This may be an unfamiliar term, maybe not. Partition global address space. The idea is that the program is aware that every node in the distributed program has its own memory, but it's organized such that you can distribute large data structures across the machine with pieces of it on every node. So in this example, a large 3D array is broken down into 6 subsections that may be on 6 what SHMEM calls processing elements and what MPI would call ranks. It's an example of an execution model, SPMD, in which all the ranks run the same program. There's some kind of job launcher like MPI run. You give it the name of the executable, and it starts up copies of that on as many nodes as you wish. So what about OpenSHMEM itself? I think for the third time now, I've mentioned that the basic operations are one-sided remote memory access, put, get, put with signal, atomic operations, fetch, both fetching and non-fetching versions, arithmetic and bitwise operations, and things like compare and swap that are useful for global locks and such like. The memory model is a little different than the model one might find in an MPI program, in that there is a region of the aggregate memory of the system called the symmetric heap. And one allocates objects in the symmetric heap, and what you get is a copy of that object on each compute node, and the program knows where they are. You can talk about your own with local access. You can talk about an object on another processing element with puts and gets that mention which PE it's on. And again, the collective operations are there. It's an active community. Currently, release 1.5 with 1.6 expected around the end of the year. A lot of the same people are involved in SHMEM as are involved in SYCL. You'll see Intel and ARM, and we also have NVIDIA and AMD in a lot of the labs and universities. So what about GPUs? I think it's not a surprise to anybody that that GPUs are attached to almost all high-performance computing systems now. For some of the ones that use Intel hardware are the Aurora machine at Argonne and the Dawn machine at Cambridge. SuperMUC is at Leibniz, LRZ we call it. And Clementina is a system in Argentina, and TAC down in Texas. There are other GPU-initiated SHMEM libraries. Everybody who makes GPUs is interested in this topic. NVIDIA has NVSHMEM that supports many of the same APIs for CUDA and NVIDIA GPUs. And AMD has a thing called RockSHMEM that is also quite similar and supports the HIP model with AMD GPUs. The current standardized OpenSHMEM does not talk about GPUs. So what's happening here is that different vendors are pushing forward to try and provide support. And I think in due time, this will all be standardized. And what we hope is that Intel SHMEM will try to position and support it as the kind of most open version of it and to support open environments like SYCL. So what is Intel SHMEM? Here's a software stack picture. The blue stuff is Intel provided software or software for which Intel has versions. Gray stuff is everybody. And the green stuff is hardware support, supporting hardware. So down at the bottom, in a distributed system, you might have GPUs plugged into a lot of nodes. You might have a high-performance interconnect, such as InfiniBand or Slingshot or RDMA over Ethernet. On the software picture, that sort of scale up is what we call it when you have a lot of GPUs plugged into a single node. And scale out is when you have a lot of nodes as well. So for scale out, we use interconnects like typically interfaced by libfabric. And for scale up at present, we are using one API level 0. In turn, in order to provide a distributed programming model on top of that hardware and runtime environment, Intel SHMEM is kind of a one-sided version. You do puts and gets. One CCL is part of one API and provides collective operations and also some point-to-point operations with a C++ style API and with a certain focus on AI applications. And Intel MPI is an implementation of MPI not dissimilar than MPitch from Argonne. On top of that level, one could have kind of higher order libraries like distributed ranges, and on top of that, application software, perhaps written in C++, SYCL, or OpenMP. So once Intel SHMEM is now in its open source release 1.0 that came out in December. There's a GitHub repo, there's online documentation. We've tested it on Intel GPUs, Ponte Vecchio, with or without Z-Link direct connect networking, and with interconnects using the libfabric providers for CXI, which is the HP Slingshot network, and for Verbs RxM, which is InfiniBand networks. Major features, 5th time, I think. Remote memory access, remote atomics, collectives, and synchronization. Right now, we are using Sandia OpenSHMEM, which is maintained by Intel, as a kind of a backing library to do off-node communications in a transparent way. And we have support for putting the symmetric heap either in GPU memory, which is the preferred location, because that's where you want the most high performance access. But you can also put it in host memory if you'd prefer, which may be somewhat easier to debug. We have a reverse offload mechanism so that when you initiate operations on the GPU that require off-node access, such as doing a port or get or a remote atomic to a different node, we pass that command up to a proxy service on the host CPU to use the regular off-node networking. And a reasonably comprehensive set of unit tests and performance tests. So what does this look like? Here is a simple example that doesn't do anything in particular, but I think the point here is that it's a pretty lightweight thing to use. It does not require a huge change in your programming mindset. You include a couple of header files. ISHMEM.h is effectively one-to-one with the OpenSHMEM header file, and an extension interface called ISHMEM-X that includes the extra functions we've added for work group in SYCL. Once the package is initialized by ISHMEM init, you can allocate objects into symmetric heap. And again, you get a copy of each of these on each PE. Then you might run a parallel kernel, and inside that kernel, you can make ISHMEM API calls, such as find out which processing element you are with ISHMEM myPE, how many there are, because of course you could run the program on a variable number of machines. And as a simple example, ISHMEM-X int quit work group is a function that copies a block of integers from the local PE to some remote PE. And the work group version of this uses all the work items in the work group to cooperate in making that copy happen. And that's relevant because in systems where you have several GPUs plugged into the same host that are connected by Z-Link, this API call actually translates into a series of stores by the individual threads, so that it looks like a big communications API, but it very quickly resolves into loads or stores. Here's a somewhat more useful example of a 2D stencil application where the perhaps large 2D array is distributed across a set of GPUs, and each update cycle, each cell is replaced by the average of its 4 neighbors. And because this is a fairly classic Halo application in distributed computing, where you have regions that overlap between each of the nodes, and when you are on one of the edges, you have to do something about it. And what this code does is if you're in the first or the last row assigned to this GPU, then you, as well as updating your local storage, you send a copy of the update to your neighbor. This is using a call called ISHMEM float P that moves a single floating point number to a remote address. And again, this is much more lightweight than it seems, because typically that ISHMEM float P after an address translation resolves into a store instruction. So we've done some performance testing on an internal cluster we have that is built out of Aurora nodes. So each one has 6 GPUs, 12 GPU tiles, and 2 Sapphire Rapids processors. And you get results that are kind of like this, which is the kind of chart that is typical of this sort of work. On the left is bandwidth, on the right is latency. This is a put operation, that put work group we saw a couple slides back. And on the left side of the slides, you see the part that is done on device. So the The different colored lines represent work groups of different sizes. More threads, more performance. At some point, it becomes more performant to switch from using loads and stores by threads to calling the level 0 copy engine mechanism, because the copy engines are designed to copy bulk data from GPU to GPU. And that gives you the single line on the right-hand side. The latency version of this is really showing that the operations are quite lightweight, about 2 microseconds for copies of up to 1,000 bytes, 1,000 bytes or so, to 4K bytes, looks like. And so the takeaways from all this are that it's available now, rather lightweight. So if you'd like to go beyond the bounds of a single GPU, this is worth a try. You can have both host and GPU initiated operations that work on either host or GPU memory. The small operations, if you're just doing individual loads, puts and gets, those are quite low latency to let you talk to memory on a different node and different GPU. And the large operations achieve the full hardware bandwidth by exploiting the level 0 copy engine hardware. I want to say a couple things about our sister groups, because OpenSHMEM is only one of several ways that you can expand beyond a single GPU. The OneAPI Collective Communications Library also supports GPU memory and lets you do collectives and point-to-point operations as well. It's got a certain amount of, it's got a C++ flavor to its API, and it is designed for interoperability with SYCL. And has a certain how would you say it? Optimizations for deep learning. Intel MPI is a standard implementation of MPI, but it has some new twists in that it supports GPU memory. So when you make these MPI calls, you can do sends and receives of GPU memory objects. And it also, in the newest release, supports the MPI-3 remote memory access operations initiated on the GPU as well as on the host, so that in a way similar to Intel SHMEM, you can do effectively loads and stores to remote GPU memory. And that is what I have. Thank you for your attention.
If we're working on an application that has to scale from a single node up to many nodes, and we want to use a solution like this, what are the implications on the performance impact of the single node case?
Typically, I think that the examples that I've looked at will have an if statement in the code at some point that says this piece of data I need to talk about local or remote. And if it's remote, you would call an Intel SHMEM operation. And if not, you can just reference the object directly. However, you can also just let the OpenSHMEM operation be there as well. It will go through a couple of if statements itself to determine whether the object is local or remote. And when it's local, it will do a load. And if it's remote but reachable by Z-Link, it will do a load. And if it's remote but not reachable by Z-Link, it would pass the information up to libfabric to use InfiniBand or whatever. So if remote, but like anything else, if remote references are small, they're not going to be as fast as you want. So that it is worth thinking about the structure of the application to try and do remote operations in bigger chunks.
Hi, thanks. So if I wanted to add support for this model with a SYCL implementation that isn't DPC++, what would that SYCL implementation need to do? Like this device-sided initiated communication, does it boil down to some additional SPLV built-ins, or what does the compiler do in that case?
We don't have a dependency on the compiler. So the features we need are the ability to call a subroutine, because that's what these are. The ability to do inline subroutines is quite helpful because that you would eliminate all this argument passing that way. And we do, in our present implementation, use SYCL global variables, which are a pretty new feature. But we only need one as a place to store the SHMEM data structures.
But you still have like a device side function, so there needs to be some SYCL library that.
Oh yes, so, I mean, what we've tested on is using DPC++ and SYCL and level 0 on Intel GPUs. But there's nothing magic about those things.
Okay.
The Intel SHMEM itself, sources are open source. You can kind of dig in and see how it works, and we'd be happy to give you a tour.
Thanks you.